specifically, we're going to be talking about mechanical energy. There's other kinds of energy like chemical energy and whatever. We're talking about mechanical energy. And what that means is like motion. So if you put something high on a shelf, you're giving it energy, giving it potential energy. If there's a skateboarder skateboarding, you know, they have kinetic energy and they're gaining and losing potential energy. Remember last week how I was talking about vectors? So we had, oops, that's the spoiler, but you could probably guess that was coming, where we had momentum marked by a P is equal to m times v, where v is the velocity and the direction super matters, and sort of for momentum, direction super matters. Energy is what we call a scalar, which means that directions don't matter. Scalars and vectors don't mix. An example of a scalar is mass. Mass is a scalar quantity because direction doesn't matter for it. Energy is also a scalar identity thing, whatever. So the first point about energy is that direction is never going to matter. The only thing you need to know about is positives or negatives. And even those kind of don't matter because the 0 point in a mechanical system doesn't matter either. I don't know. Have you guys started talking about energy yet? Like, could you define what the equation for potential energy is, or gravitational potential energy? Yeah, MGH. Where h is the height of something above the surface of the Earth. But, I mean, think about it, right? The Earth is freaking huge. There's like kilometers and kilometers of stuff leading to the center of the Earth. Why don't we calculate this? Why don't we calculate the radius of the Earth when we're talking about potential energy? Why do we only care about this h? And the answer is we just don't give a shit. We don't care. The 0 point in a mechanical system doesn't actually matter. So what that means is we will just define this spot right here on the surface of the Earth as 0 potential energy, gravitational potential energy. And then from there, we'll count up. If hypothetically, you know, like over here in the Earth, we dug a hole that was like 10 meters deep, something down here could have negative potential energy. Because our reference is here. And if that's the case, we can look at a problem like this and just be like, okay, why don't we define this spot as our 0 potential energy spot? So how does it work with valleys and mountains? I'm not sure if I understand the entirety of the question, but if it has to do with like where you're setting the potential energy spot, then yeah, you can just put it wherever you want. Like nothing is stopping us from doing this problem right here with the center of the sun. So like, what's the gravitational potential energy from the sun? And then everything would be like negative 10 times something to the negative, or I don't know. It's something insane. And there's no reason we would do that because it's stupid. But we could hypothetically do a problem in that way. So the 0 point doesn't matter. So we can always make our energy systems positive, so that our kinetic energy and our potential energy are never negative. Like I said right here. This is a serious distinction. This right here, delta E, is the change in energy. This is not the absolute value of energy. This is not the energy itself. This is how energy is changing. If something, let's see, starts up here at 5 meters high and then ends down here at 1 meter high. And let's say the object is 1 kilogram. What is its U, its gravitational potential energy up here? And I'll call this UG1. You know what? And to make it even easier, let's just call the gravitational acceleration 10 meters per second squared. Hey, look, 10 times 1 times 5 is 50. The second one is 10, and these are units of joules. This is 2. If I'm doing the delta U of that system over there, that's U2 minus U1, which is equal to 10 minus 50, which is equal to negative 40. We lost potential energy. We expect this. Your negative, your delta E's, your delta U, your delta K, we'll talk about this in a second, you can expect those to be 0. Yeah. So I'll just review gravitational potential energy. U is equal to mgh. An equation that we can show for the delta U is mg delta h, because the only thing that's changing is the height, which is just h2 minus h1. You can always just pull these things out of the equation. So you'd have to do less work. I don't think there's anything else I need to say about this. We can set our 0 line wherever we want. That's where we're saying that h is equal to 0. So we can either say it at the surface of the Earth, we could say it at the center of the Earth, we could set it like at the top of a skyscraper or something. It doesn't matter. You get to choose that. Kinetic energy, this one will never be negative ever, because it has a squared involved with it. You will see this most of the time as K. If you guys are engineers, in your upper level courses, you might see it as T, but I feel like every time we see it in Physics 1, it's always K. And the equation to find it is 1/2 mv squared, where m is the mass and v is the velocity of the object, and then we take that value and we square it. If we're using an equation to calculate the change in kinetic energy, this can also be negative. It's just 1/2 m, and this is the delta of the v squared. This one's weird. You have to square them first and then subtract them. If you are doing, like, let's say an object is going 10 meters per second and then it's going 5 meters per second. If you were doing 1/2 m 5 minus 10 squared, wrong. That's not how you spell wrong. You instead have to do 1/2 m 5 squared minus 10 squared. These are not going to be the same answer. This power is not distributive. It cannot go to both of those. So be very, very careful when you're doing these. But as we can see, this one is going to be negative. We started going slower, and so therefore the velocity or the kinetic energy has decreased. Now we're going to talk about the conservation of energy. Remember last week when we were talking about collisions, and if something collided and it wasn't 100% elastic, then the kinetic energy decreased? That's because that energy has to go somewhere. Energy cannot be created, nor can it be destroyed. It just changes its form. In those situations, the energy was lost to maybe like breaking the wall a little bit. Maybe some of it was made into sound or heat or whatever, but that energy always went somewhere. Same thing happens with mechanical energy. What this is saying right here is that the total mechanical energy of something will equal the final mechanical energy of something. That's what this prime means, is the second, the final. AKA, the change in mechanical energy is always going to have to be 0. So let's define what mechanical energy is in this case. Mechanical energy is an object's kinetic energy plus its potential energy. So, I mean, I didn't write this down, but it's just 1/2 mv squared plus mgh. And that is its total mechanical energy. So the change in total mechanical energy is the change in the kinetic energy plus the change in the potential energy. And you can see that those equations were put together right here. So let's put things together, because we have this equation right here. Our first kinetic energy plus our our first kinetic energy plus our first potential energy should equal the sum of our second kinetic energy plus our second potential energy. And those equations look like this. Now, this is assuming that there is no friction. If there is friction, we will introduce a new kind of mechanical energy, that there's no easy way, there's no equation for it. Actually, no, there is an equation for it. I just don't know it. That's thermal energy. This is like, you know, when you rub your hands together and the friction starts heating them up, that's energy being turned into heat, thermal energy. So if you have a system, like say you're measuring a ball rolling down the hill, and its potential energy, its total mechanical energy, its K1 plus U1 does not equal K2 plus U2, that means that there's some thermal energy in the system. And whatever the difference is, that's just what it is. Are there any questions about these concepts? Would it be at all helpful to you all if I did an example problem using energy? And if your answer is no, and you'd rather just move on, yeah, let me know. Okay. Overwhelmingly, yes. Excellent. Okay, so let's say we have a setup where we have a ramp and a ball is moving down the ramp at different times. So what maybe a question is asking is, what are the K and U at each point? I didn't give this ball a mass, but why don't we call it just 1 kilogram? Make our math easy. So I'll do it. Yeah. So the potential energy at point A is equal to mgh, and I'm just going to use g is equal to 10 for this example. During the lab, please use a more correct value. So 1 times 10 times 5 is 50 joules. That's what the potential energy is up here. Maybe we start at rest. So this thing isn't moving yet. So its kinetic energy at point A is equal to 0 joules, because 1/2 v squared, where v is 0, is just going to be 0. What is the total mechanical energy in this system? So I'll say E, and this is just going to represent the total energy, is equal to UA plus KA, which is equal to 50 joules. That is how much energy is in our system. So what now it's going to ask is, what are some of these things at point B? And what if it gives us the question and it doesn't tell us the V? Because we could very easily, take a speedometer and calculate 1/2 mv squared here. But what if we don't have that information? We can still get the kinetic energy. And in fact, we can get the kinetic energy much, much easier. And then from there, calculate the velocity. So remember, E is equal to E prime. So that means that EA should be equal to EB. And I'll expand them out. Our UA plus our KA should be equal to UB plus KB. Well, we already know what UA plus KA is, right? It's 50 joules. We can quickly calculate what UB is. It's MGH, so 1 times 10 times is up here 2 meters. And then we don't know what the kinetic energy is yet. We'll do some arithmetic. We get 50 joules is equal to 20 joules plus the kinetic energy. And then if we move this to the other side, we get that the kinetic energy is equal to 30 joules. If the problem is just asking for that, you can stop there. But if you wanted to go a little bit further, let me clean up some of this. We know the equation for velocity and kinetic energy, right? So I'm going to change colors just so we're not confused. We know that K is equal to 1/2 mv squared. So if we know the K at B, so I'll just call this KB and VB, 30 joules is equal to 1/2, and then I'll plug in for M, which is 1, and then VB squared. I'll move everything to one side. So it's 60 joules is equal to VB squared. And then I just take the square root of this. So VB should be equal to the square root of 60 meters per second. I don't have a calculator nearby me, but if I was actually doing this problem, I would plug that into a calculator and get a better, closer answer than square root of 60. All right, let's move on. Let's look at point C. So remember, the energy at part B should be equal to the energy at part C. So 50 joules should equal to U3, or UC rather, UC plus KC. All right, we'll plug in for U. So MGH, it's 20 joules plus our KC. This is just the same answer that we found before. But what if there's friction? So there's not friction here. This is really, really slick. There is friction here. And let's say that the problem tells you that KC is, let's see, what would be a good value? Let's call it 25 joules. We can see that 50 does not equal 20 plus 25. That means that there's a thermal energy in our system. So 50 joules should be equal to U3, or UC plus KC plus, and I'm just going to call this E thermal, ETHC. And so that would be 5, and we can figure that out ourselves. Then we can do the same thing for point D. I'm not going to do it right now, but it should be easy to see that the potential energy at point D should be equal to 0. And so all of the energy will either be back at the horizontal space in the thermal energy, or it should be in kinetic energy. Are there any questions about this? Does this, I mean, okay, instead of asking questions right now, scale from 1 to 5, how confident do you feel in doing a problem that would be similar to this? Okay, so fairly confident. Hopefully the lab will further cement that. Because there is one section of the lab that is essentially doing this problem, but instead of it being a ramp that just goes down, it's a ramp that goes down and then back up. And you'll be calculating, actually, I think it's a ramp that like goes down, comes up partially, and then goes like all the way down. And a lot of people try to do that problem by like doing the 1/2 mv squared and blah, blah, blah. And it's a mess. And it's just harder. There's an easier way to do those problems. And it's the way that I just showed you. Yeah, now are there any questions before I move on to showing you the lab? To be taking measurements on a skate park as people are going up and down skateboards tracks, I guess. There are 3 sections that we'll be using: the intro section, the measure section, and the graph section. I have not really done much with the playground section, so whatever. Be very careful with which section you're on. The lab is pretty explicit where you need to be. Things that you can do in the intro: you have a person, you can click up, you can put them on a spot, you can see them go back and forth. You can find a graph of the energy. You can see that the total energy is never changing, and the kinetic and the potential energy are just going back and forth. If I turn the friction slider up a little bit, we can see that the total energy remains the same, but the thermal energy increases, while the kinetic and potential energy progressively get smaller and smaller and smaller. You can change the mass of the person, so you can change them to be absolutely huge or itty bitty. You can change the gravity, but you don't need to do anything with that. You can see what their current speed is. This is not with positive or negative, so it's just their absolute value of speed or velocity. That's pretty much it. There's a couple other tracks that you can choose. There's not going to be a whole lot that you'll do with this lab, but notice that there's an option to change the reference height. We won't be using this, but this is just proof that I can just set my negative energy. And if I set it, or if I set my 0 potential energy here at the top, you can see that the graphs, the potential energy is always negative, but the kinetic energy is always positive because it can never be negative. But that makes our problems harder to work. The measuring tool is the one that you'll be using the most. As the person goes back and forth, you can pause them at your whim. You can take this target and put it over one of the dots that she leaves behind, and it will tell you exactly what her current potential kinetic and thermal total energy are going to be in those spots. There will be some things that ask you to calculate, like at the bottom of the parabola. Just get it as close as you can. You can see that this one's off by a little bit, but if I put it here, the potential energy is 7.3 compared to the kinetics 3,000. That's fine. That's close enough. Again, you can change the mass of the person. You can change the friction. You can add or subtract it. You won't use this quite as much, but I think this one is the most important because it shows you actual values. There are two graphs that you can look at. There's the position, the energy versus position graph, and there's the energy versus time graph. And you can actually see what it looks like. This is going to straight up give you some of the answers to this right here. And that is kinetic energy looks like the opposite of the track. Potential energy looks like the same shape as the track. You can see that potential energy is a parabola, while kinetic energy is an upside down parabola. And if I do a weird looking one, you can see the exact same thing. Yeah. The time graph right here, if I start somebody and I hit play, you'll see how their energy changes as time goes by. You're asked to like measure the energy values based on the graph at certain times. You can, this one sucks. You can see that there's no numbers between 3,000 and 1,500. My recommendation is put your time as close to the time you want to take. So if I'm taking, let's say 7 seconds, which is in between 6 and 8, I'll just keep pressing plus until my value is very, very close to the top. So the potential energy or the kinetic energy here is about 1,500, and the potential energy is like, yeah, call that 900 or something like that. You're going to have to eyeball this a lot, but there's ways that you can make it a little bit more accurate.